Okay guys, the next thing we're looking at now is stationary points, okay? So if you recall, what we've been focusing on is derivatives and the rate of change of the function, right? So now we're going to, instead of looking at the rate of change of the function as a whole, or how the function behaves as we move across the x-axis, we're now going to look at the behavior function at a specific point, particularly at stationary points. Before we do that, I want us to think of three ways the derivative could be, right? So say you have the function f of x squared, right? And we've got our Cartesian plane, and let's just say that the function turns on the stationary point. Sorry, turns on the origin. And we can have, that's the only x-intercept, right? It also happens to be the only y-intercept, because it's on the origin, right? Now, if we have to look at this function, alright, we're going to look at the derivative first, and using the power rule that we've already learned, the derivative is just 2x, right? What we can see here then, computationally, to make this negative infinity and this positive infinity, what we can see from computation is for all numbers, you know, if we plug in an x, so this is how the graph or the function in general behaves, or the rate of change of the function. So if we want to look at a specific point, we can plug in any point x. But we can see here that if we take any point to the left of the origin, so any point as x tends to infinity, negative infinity, the derivative of the function is going to be negative. So in other words, the derivative of x less than 0 is going to be less than 0, or negative, right? On the other hand, if we look at this side, if we take any number that's to the right of the origin, so any x value that's positive, you know, as x tends towards, or x greater than 0, and tends towards positive infinity, what we'll see is the derivative of any x that's positive is going to be positive. But what does that actually mean by saying that the derivative is positive or the derivative is negative? What do you notice about the function at those 2 points that we've said? So we said at points where the derivative of the function is negative, at all those points we've seen that the function is doing this, right? And all the points where the derivative of the function, is positive, the function is doing this. So clearly here we can see the function is decreasing, and here we can see the function is increasing. So what that tells us is when we've got a negative derivative, the function is decreasing. If we've got a positive derivative, the function is increasing. In other words, the tangent, if I had to draw several tangents, here, see there's a tangent, 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 there's a tangent. Here you can see the tangents on the left are like this, and the tangents on the right are like this. So these tangents are clearly positive. The rise is positive, and the run is positive. Whereas here, right, you can see the rise is still positive, but the run is now negative. And so those tangents will be negative, which makes sense because the derivatives will be negative at that point. But we see that those aren't the only points. There's a point here where the tangent is horizontal, right? And if the tangent is horizontal, what do we know about the tangent of a horizontal line? Sorry, the gradient of a horizontal line. Well, we know that the gradient of a horizontal line is rise, which is 0, over run, which will be whatever the distance is. So the gradient is 0. So for a horizontal tangent, the derivative is 0. So at this point, here, on the turning point, the derivative is 0. So if to the left of the stationary point the function is decreasing, and to the right of the stationary point the function is increasing, at that stationary point the function is still. The rate of change of the function is 0. In other words, all points where the derivative is 0, we call those stationary points because the function is still. But there are many types of stationary points. But we're going to look at 3 types of stationary points. We're going to look at types of stationary points. 3 types we're going to look at are maxima, or max, minima, or min, and points of inflection that are sometimes referred to as saddle points. And they kind of look like this. And this. That's probably a little bit trickier to you, but it'll make more sense as we explain it. So I want you to first think of these 3 types: maxima, minima, and points of inflection. So this is the maximum, this is the minimum, and that is the point of inflection. Okay, so now let's get into them a little bit. All right, let's find out a little bit. So I said the image I drew for the maxima, right, was this. So what does this tell us? So what can we see of this function if we analyze it the way we were looking at them earlier? So this is the stationary point. Let's draw the line of symmetry. We know for quadratic functions there's a line of symmetry. And so we've drawn this line of symmetry, and we see that as a function goes from negative infinity, so as it it approaches the stationary point from the left, or from negative infinity to the stationary point, we see that the function is increasing. So in other words, we have a positive first derivative, and then it approaches, and touches the stationary point, and from the stationary point, as x tends towards infinity, we have a negative first derivative. So I'm going to get into this in more detail, but this is one way of identifying the one of the 2 main ways I'm going to teach you how to identify stationary point. But this is, to classify stationary point. This method is a graphical method. It would involve finding a stationary point, then plugging in values to the left of the stationary point, seeing what the derivative is at that point, and then assessing the derivative of the function to the right of the stationary point. And then you'd see that if it goes from positive to negative, positive, 0, then negative, so if the derivative of the left of the stationary point is positive, the derivative by definition at the stationary point is 0, and to the right of the stationary point is negative. Then what this tells you is that it must be a maximum, the stationary point. But that's one way. Another way, I'm going to go into more detail about these ways, but I want you to understand why they work first. Another way of identifying it is thinking, well, if the rate of change is going from positive to negative. So another way of thinking about this is saying that if the first derivative is positive before the stationary point and negative after the stationary point, so the rate of change, if we look at the second derivative, the notation being d2, so the second derivative of y with respect to x, or another way of writing this is f double dash of x, all mean the same thing. This is saying the rate of change of the rate of change. Right? That's what we're trying to think of. So if the rate of change is going from positive to negative, what does that tell you about the rate of change of the rate of change? Well, what that means is the rate of change of the rate of change must be negative. Because if the rate of change is going from positive to negative, it must be negative. It's a similar way of saying that if you had an upside down parabola and the value of the function is increasing, so going from positive, then still 0, and then going to negative, right? It goes from positive, right? And then it goes to negative, then the function, right? The derivative of the function is then increasing at some points and then decreasing at other points. Well, if it goes from increasing to decreasing, then it must overall, the rate of change be negative, be decreasing. It's going from an increase to a decrease. So you can look at the second derivative, and you can note that if the second derivative at the stationary point is negative, then you know you must have a maximum, because the rate of the change of the rate of change is negative. So in other words, the function is going from positive derivative, first derivative, before the stationary point, to a negative first derivative after the stationary point. To take this even further, what this really means is if you have a quadratic function and the second derivative is negative, the function you have is concave. The entire function is concave. And so that means that the stationary point, the point of stillness, has to be a maximum because of the shape of the graph. It's concave. Okay, now let's look at minima. Okay, now we're going to look at minima. And the image for minima, I said earlier, was like this. Much the same, we do the line of symmetry. Now we see that the derivative of the function, as we move from negative infinity, if I had to, I move from negative infinity to the stationary point, is decreasing. So it's negative. And as you go from the stationary point to positive infinity, it's positive. And at the stationary point, by definition, it's 0. Meaning the function goes from negative to still, so decreasing to still to increasing. So the tangents will be like this, right? Negative, then still, then increasing to positive. So what that means, we can use this to determine that's a minima, right? If before the function, it decreases to the point, to the station, before the stationary point, it decreases to the stationary point. After the stationary point, it increases, then clearly the lowest point it can be is the stationary point. It doesn't decrease past the stationary point, right? So the graphic way of solving for it would be saying, okay, plug in values. If before or to the left of the stationary point, the derivative is negative, and to the right it's positive, and obviously 0 at the stationary point, then you've got a local minimum. But again, we can think about, well, let's think about the second derivative. What is happening? Well, conversely to what we saw earlier, the second derivative is now moving from negative to positive. Sorry, the first derivative is moving from negative to still to positive, meaning the rate of change of the rate of change has to be positive. Overall, the function moving from a negative derivative before the stationary point to a positive derivative. So if the second derivative at the stationary point is positive, then you know it's a local minima. And to take that even further again, what that tells you is if you've got a quadratic function and the second derivative at the stationary, if you've got a quadratic function and the second derivative at the stationary point is positive, what that tells you is the function is convex. So it has this shape. The function is convex, which means if the function is convex, what that tells you is that any stationary point must be the minimum. And why we say it matters that it's a quadratic function is, if you think about it, let's say the basic form of a quadratic function is x squared, right? And the first derivative will be 2x, and the second derivative will be 2. So if you have a function that's quadratic, so of degree 2, the second derivative is going to be a constant. And so if the second derivative is a constant, it means second derivative is the same at all points on the function. So if the second derivative of a quadratic function is positive, the function is at all points convex. If the second derivative of the function is negative, It means the function is at all points concave. That's why you have a maximum there. It's also why we'll speak of the term global maximum and local maximum just now, but it's also why for a quadratic function, you know that the local minima or local maxima is also the global minima or global maxima, because the function is at all points concave or convex, depending on the nature of the second derivative at the stationary point. Okay, so the third type of stationary point is a little bit more complicated, but is a point of inflection, or saddle point, as we spoke about earlier. So when you think of saddle, you should think of like a hump of a camel. That's what the saddle point idea is. So you've got two maxes and sort of a saddle. But yeah. So the point of inflection is a stationary point, and it's different to the other two stationary points because the other two stationary points can be thought of as turning points, right? And the reason the other two stationary points can be thought of as turning points is because in both cases, right, where the maximum min, the derivative of the function changes sign, either from negative to positive or positive to negative, as it goes through and past the stationary point. Whereas, as you can see in this example from the cubic function, the derivative of the stationary point is constant. It doesn't change. So whatever the derivative of the stationary point is here, it's positive. The derivative of the stationary point here is also positive. As you can see, it's not strongly positive, but it's increasing before, still increasing after, and continues to increase. Unlike here, where, if I clean this up a bit, where we have a maxima, here, the function increases, hits the maxima, decreases. If this function had started increasing, then hit the function and decreased, then we'd have maxima, but it stays the same. So what we have here is the point of inflection. Another perhaps helpful way that some people like to think about it is you can think about it in terms of concavity. If you look at the point of inflection, it is a change in concavity before and after the stationary point. So here, if we had kept this function as the parabola, you can sort of see, if you carry on drawing here, you'd have a parabola of this shape, right? The general shape of the function in the locality of the stationary point, like as it approaches the stationary point, the general concavity is concave up or convex, right? It generally looks like this, which is, as you see with convex parabolas, part of that. But as we go past the stationary point, as we go past the point of inflection, it starts to look like this, which is, it starts to look like this, which is part of a concave down or concave parabola. Alright? So, as you can see in this cubic function, the graph, as it goes to the point of inflection, or as it approaches the point of inflection, has it's convex, the general shape in the locality, and past it is concave. So the point of inflection can be seen as a change in concavity. So because of that, those two reasons are the fundamental logic behind the two ways of finding a point of inflection. So graphically, since the rate of change of the function doesn't change, what we know is that the first derivative of the function before and after the stationary point will be the same. So in this case it will be positive, 0, positive, if this is the derivative of the function at various x values. So this will be stationary point value, this will be values to the left of it and values to the right of it. Right? It would remain, well, in its locality, would remain positive, 0, and positive. So we can tell if you have a stationary point and in its locality, or the nearest points, are positive to the left and positive to the right, or negative to the left and negative to the right, then what you know is you have a point of inflection. But similarly, because both sides don't change right? So because to the left and right of it, the derivative of the rate of change doesn't change, what that tells you is that the rate of change of the rate of change also doesn't change, right? So if you go from plus to plus, the change here is 0. So if we look at the second derivative of a stationary point at the station of the function at the stationary point, and you find out the value is 0, then you know you've got a point of inflection. Learned to an example. Call an example. See, in this example, we're going to find a minimum and a maximum. We're not going to find a point of inflection. But if there was a point of inflection, we just do the same thing, and I'll show you where it would be different. Okay. One thing before we start finding and classifying the stationary point is it's always important to remember that this is for cubic functions. If we're doing it for parabola, the method is a lot easier. So if you had a parabola like this, for example, and you knew the 2x intercepts, then you could just use the equation of symmetry. So you take the 2x intercepts, and it's 2 and 6, say for simplicity, then you just say the 2x intercepts, add it together, divide by 2, in this case you get 4. Take that x intercept, you plug it into the, or that x value, plug it into the function value, so you get f of 4, and you get out something. Then the stationary point, in this case, would be 4 and f of 4, and it's the function evaluated at 4. And you can look at the leading coefficient. In this case, you can see it's a smiley parabola or convex parabola. So you know the leading coefficient is going to be greater than 0. And these two pieces of information will tell you that you've got a stationary point here at 4 and f of 4. And it's a smiley, so you know it has to be a minimum. And you know that it's a quadratic, so the function is convex always. So clearly, this minimum is a global minimum. So what that means by global is that this is the minimum value of the entire function. You cannot go below this. So if we look at this, you don't even need calculus to solve it with the parabola. You could just use analytically, provided you've got the 2x intercepts. So you could just find the 2x intercepts and go from there. If you wanted to, of course, you could just set the first derivative of the function equal to 0 and look at the second derivative and then classify, like we'll do for cubic functions. So I just wanted to let you guys know that if you've got a parabola, I often find that using the calculus method is actually quicker, even for a parabola, but if you've got a parabola and the question asks you not to solve using calculus, or if you, I don't know, just not as comfortable with the calculus method, there's another method for you to do it. But let's use calculus here, and you must remember, for a cubic function, there's no equation of symmetry. So, unfortunately, there's not much you can do with that. So I know the nature of this graph, which I'll draw on the bottom here. But remember what I said about endpoints? So you can see there's a positive coefficient here. You can see it's a cubic point. You know it's going to go through the quadrants 1, 2, and 3. So you know, generally, you're not quite sure if there's going to be a point of inflection or if there's going to be a max and a min. But let's just assume there's a max and a min. I know there's a max and a min, but just for your sake, you can know that the function has a general, sort of a general shape like that, or general form. And you know that just using end behavior that I showed you earlier. See how it can be useful. But yeah, so when you ask a question like this, it's actually two parts. Part 1, find. Let me switch. Remember, in this question, there's two parts. There's find and classify. Two very different ideas. So let's start with find, by far the easiest part. As I said earlier, by definition, a stationary point occurs when the function has a derivative of 0. So step 1 is to find. Alright? And to find, what do? We set dy dx, where this function is f dash of x, and we could say dy dx or f dash of x is the function. And we're going to use the power rule here, because like I said, it's a much easier way to do it. Again, you could evaluate using first principles, but that would be very long. So yeah, we're going to use the power rule. So remember the rule, so 3x squared here, and minus 3, and of course 7 is a constant, so that just fades away. Oh, 7 is a constant, so, sorry, fades away. So we've just got 3x squared minus 3 as the derivative. And the next step is to evaluate the derivative at 0. Now, an important thing, a notational thing, that often can lose you marks in exams, because it is technically a mathematical violation. Often, students will go to the next step and just say, 3x squared minus 3 equals 0. Eventually, you'll work out the station point and everything will be fine. You've got the right idea, but you've got about it wrong, or wrongly, because, of course, the function can't be, the derivative of the function can't be 0 at all points. Right? We can clearly see it's positive some places, it's negative, etc., etc. So we've got to evaluate the function at, we've got to let that function be 0. So what I would do, you can word it how you like, but I'd say to find stationary points. Another one to be concerned about is I'm not sure what teachers or regulations will be about abbreviations. I usually just write STY-PEAT. Like I know my university accepts that, so just find out what you'll be allowed to do. So to find station point, let f dash of x equals 0. This is nice for the marker because the marker also knows that he knows you know what you're doing. You're telling him, even if you get the method wrong somehow, at least he knows you know what you're supposed to do. So we set the first derivative equal to 0. In this case, you say 3x squared minus 3 equals 0. We can obviously divide 3 by 3, so we've got x squared minus 1 equal to 0. Another thing to realize here is also, if you've got a cubic function, the derivative of the function is going to be a quadratic function, and so on and so forth, according to the power rule, because of that a minus 1, right, in the powers. So just something to know. So we've got x squared minus 1. This is clearly the equation of a quadratic. There's two ways to solve this. You can either say x squared equals 1, therefore x equals plus or minus 1. I find that the easiest way. Remember, when you're square rooting, you want to take plus or minus of the answer, because negative 1 and positive 1 squared would both give you 1. So that's one option. The other option that I find a bit tedious is you can factorize if you find that easier. Obviously, x squared minus 1 equals 0. If this is another way of thinking about this is a parabola, right, with some equation, and on the x-axis is the derivative of the function, right? So you want the derivative of the function to be at 0, right? So, sorry, I told this badly. You want the derivative of the function to be at 0. So you want to find at what points, sorry, this is horribly drawn, but you want to find at what points the parabola cuts the x-axis, right? That's another way of seeing it, of what you're trying to work out right now. So another way of doing it is just factorize it. So you can just say x plus 1, x minus 1 equals 0. Obviously you're going to get x equals plus or minus 1. Same thing, just other ways of doing it. So what does this tell us? Another mistake that students make. This tells you the x coordinates of the two stationary points, right? So to find the y coordinates of the two stationary points, what you need to do now is you need to look at the original function over here and plug in the x values to find out what the y coordinates of those stationary points are. Because obviously the stationary points lie on the curve. So what you're going to have is f of negative 1, and that's going to be negative 1 cubed minus 3 into negative 1 plus 7. So you're going to have negative 1 plus 3 plus 7, and that's going to give you 9. That's the y coordinate. So we can evaluate f of negative 1, and if you guys calculate, I'm sure you'll find it is 9. Alright? So you obviously just plug in negative 1 as a function, and you'll get out 9. So the coordinates we know, so we can conclude, alright, we're not completely concluded, but therefore we know stationary point at negative 1, 9. Again, find out how your teacher wants you to format it, but that's one way. And we know that there's another stationary point at 1, right? So another stationary point at 1, so we say f of 1 is going to be equal to 1 cubed minus 3 into 1 plus 7. We have 1 minus 3 plus 7. That's obviously going to be, you guys can see, that's going to be 1 minus 3 plus 7, and obviously going to be 5. And so we know that there's going to be, oops, there's going to be another stage point and 1, 5. At 1 and 5. So we've done the first step, we found the 2 stationary points. Now we move on to the second step, to classify them. And like I told you, there's 2 ways of classifying these 2 stationary points. So, we've got to classify. So there's 2 stationary points, negative 1, 5, and 1, 5. You guys can see that, okay? Now we need to classify them. So you can either classify, I'm going to go through both methods for both of them, but classifying, the sort of first method that I wouldn't recommend doing often, like using it, but it's good to understand it because you can think about it, you can always return back to it, and you can sort of think about what's happening. And it works with cubics because you have a general idea of what the graph looks like. So this method is solved graphically. It's kind of like the first principles of cubic functions. First principles in the sense that it's like the basic thing you look at, not that it has the same form. Graphic method. So to solve graphically, I'm going to be blocking it for now, but it'll come out just now. I'm going to draw a table. In that table, I'm going to have x, and then I'm going to have f dash of x. Okay? So we've got the 2 points, negative 1 and 1. So what's important when drawing a table is that you've got a point to the left and to the right of the 2 points. Right? So obviously a point to the left of negative 1 would be negative 2. Oh, sorry, I was supposed to write this out in red. I'm going to do this in red, just for you guys, for your mental pictures. So like I was saying, the important thing with the table is that make sure you have a value to the left and to the right of the 2 station points, in this case negative 1 and 1, or negative 2, 0 and 2. And the point is to evaluate the derivatives of the functions at the points. So if you think about it, remember I told you there's 2 ways to classify stationary points. The graphic method is really thinking about the first way of classifying stationary points. And that's looking at what happens before, it was assessing the first derivative of the function before and after the stationary point. So, well, that's what we're going to do. So first derivative of the function, as we found out earlier, f dash of x is 3x squared minus 3. So, in this case, at negative 2, we're going to have, so f of negative 2, it's going to be 3. So negative 2 squared will be 4. 3 times 4 is 12. 12 minus 3 is 9. F dash of negative 1, we already know is 0. F dash of 0 will give us negative 3. F dash of 1, we already know is 0. F dash of 2 will give us 2 squared is 4. 3 times 4 is 12. 12 minus 3 is 9. Excuse me, it's cool. So what do we know? At negative 2, the first derivative is positive. At negative 1, it's 0. At 0, it's negative. At 1, it's 0. At 2, it's positive. So let's look at the 2 station points individually. So the first station point at negative 1, 9, the behavior of the function in the locality of the stationary point is the first derivative goes positive, 0, negative. What does it mean again? If it increases towards the stationary point and decreases away from the stationary point, right? So we can even draw it if we want to make it obvious. We can draw it like this. So think about when it's positive, like this, with 0 to horizontal, it's negative, it's decreasing with 0 horizontal, positive increasing. And so you could draw the function like this. So increasing, horizontal, decreasing, horizontal, increasing. And that kind of gives you, not as good a picture, but a similar, just because the line's a bit longer, but you kind of get what we're doing here, gives you a similar picture to this. Right? And what we saw is that negative 1, 9, the function went positive, 0, negative, so it went increasing, 0, so still decreasing. And what does that tell us? It's a maxima. Right? Function increases, stays 0, decreases. And you can see here that the first stationary point is clearly a maximum. You know that's true. We evaluate the second stationary point, 1, 5. Here we can see that the derivative in the locality of the stationary point goes negative, 0, positive. So it decreases, then is still, and then increases. So clearly we have a minima because it decreases, still increases. So that's a minima. So that's the first way. So we knew we had two stationary points, so we classified two stationary points. If it was a point of inflection, what would happen? What was the point of inflection? Imagine if the second derivative here was a negative 3. Imagine it was 3. And what we had was 9, 0, 3 in the locality of the stationary point here at 0. Well, then we'd have positive, 0, positive. So the function would look like positive, 0, positive. So the graph would look a little bit like, and here you'd have a point of inflection. So that's how you'd use the graphical method to find the stationary point. So now let's have a look at the second derivative method, or the calculus method. Well, not really the calculus method, let's just call it the second derivative method. Okay, so guys, the second method that we're going to look at, the second derivative test. Like I said, the first method is the first principles. You always look back at the first method to check, that you understand the concept, etc. But the second derivative test, just like the power rule in reference to first principles, is by far the most used method, just because it's much quicker. But I would encourage you to be familiar with the first method so that the second method makes a lot of sense. So, like I said, the second derivative test is very much linked to the first method. So, to keep it simple, if the second derivative, and this is the second derivative test, if the second derivative is positive at the stationary point, then you have a minima. If the second derivative is negative at the stationary point, then you have a maxima. If the second derivative is 0 at the stationary point, second derivative is 0 at the stationary point, then you have a point of inflection. Right. Let me draw that one a little better. Then you have a point of inflection. So, and the point of inflection is there, max is there, minimum is there. So that's an easy thing to remember. If you just remember this, that is the second derivative test, essentially. Alright? But how it links to the first one is quite simple. If we're looking at the rate of change, being positive, if you recall, if it's a minimum, then the derivative goes from positive, 0, to negative, so it goes, other way around. It goes negative to 0 to positive. In other words, it decreases, stops, and then increases. Right? So clearly, if something goes from negative to positive, right, in the ends, then the behavior in general, so the rate of change becomes positive. And so if you look at the second derivative test, it's positive, then you know it's a minimum. Similarly, or conversely, I suppose, if For a maximum, the rate of change is positive, 0, then negative. And clearly, if something goes from positive to negative overall, then the general behavior is negative. So if the rate of change goes positive, 0, negative, the rate of change is negative, and you've got a maximum. And you can see here, when the second derivative, or the rate of change is less than 0 or negative, then you've got a maximum. And lastly, on the same token, if the rate of change goes from either positive, 0, positive, or negative, 0, negative, then what you have is clearly no change. Right? It's remain the same when positive, positive, negative, negative, no change. If we've got a saddle point, a point of inflection, and here we've got a point of inflection. Similarly, we've got the change from a convex function to a concave function. That might be clear if I draw it a bit like that. Alright. So yeah, that's the second derivative test. And so let's take our two stationary points and apply the test. So the second derivative of x, if you call the first derivative of x, well, let's just rework that out actually. First derivative of x was 3x minus 3. Therefore, it was 3x squared minus 3. Therefore, the second derivative of x is just 9x. So if we evaluate that at the point -1, the second derivative -1 is negative. Therefore, the stationary point -1, 9 is a local minimum. If we look here, the other point, f dash of 1, is just 9. Sorry, this is -9, +9. And therefore, the stationary point at 1, 5 is a local minimum. So here we're supposed to read a local maxima. So we can check it again. If the second derivative is negative, max, second derivative is positive, min, and we can look again at the function. The first one, or the one that corresponds to -1, is clearly a max. The one that corresponds to 1 is clearly a min. It all makes sense. That's also what we got in the other test. Awesome. So there's one other concept that you guys might have noticed that I've implicitly snuck in here. I'm going to slightly extend the syllabus, very slightly, but just so you kind of understand why it's true. Okay, so if you've noticed here, I've written the terms local. Right? It's sometimes referred to as relative. Relative. So why is this a local max? Or is this a relative max? Or a local min, or a relative min? Well, if we look at the function, right, the idea of a maximum and a minimum, right, the terms themselves, right, would mean the highest point or the lowest point. Well, clearly, this point here is not the highest point of the function. The function clearly has points that are higher. I mean, the function tends to positive infinity. Similarly, this point here is not the lowest function. The function tends to negative infinity. But what they mean is that in this general locality, in this general area, right, this is the highest point. It's the local max. Here, in this locality, this is the lowest point. It's the local min, right? Another way of thinking about it, or I guess if you want to say relative to this part of the function, this is the highest point. Relative to this part of the function, this is the lowest point. So that's the concept. Another way to think about it is, if you think about your school, your family, think about who the tallest person is, right? You might find that you're the tallest person. Now, it's one thing to say that you're the tallest person in your school or your house. It's another thing to say you're the tallest person in the world, or the tallest person in history. That's sort of the same concept. You might be the tallest person relative to your school, or in your local area in your school, but you're not necessarily the global or the absolute tallest, you know? You might not be the tallest person in history or in the world, right? So that's sort of the concept. So you might ask yourself then, with a function like this, what is the global max, or what is the global min? Well, in this case, well, actually, before I say that, I want to tell you why something can be a global min or a global max. There can be two reasons why something can be a global min or a global max. In fact, I'm going to use a different color. The two reasons why something can be a global min or a global max are, one, similar to what we said about looking at the behavior of the function, end behavior that we looked at earlier. There's endpoints. And the second reason would have to do with concavity. Right? So, this function, right, so as I was saying, the two reasons you could have a global maximum, the two reasons are an endpoint or concavity. Now, what do I mean by this? So the endpoint, as we were explaining in end behavior that we studied earlier, the endpoint is how the function behaves in extremes. In this case, the function tends to negative infinity, and the function tends to positive infinity in its extremes. Clearly, there can be nothing by definition lower than negative infinity, or anything greater than positive infinity. So technically, the global min and global max of the function are negative infinity and positive infinity. But so many functions tend towards those, and they're such abstract concepts, we just say that there's not really a global minimum or a global maximum, usually. Alright? But if for some reason, say for some reason, and like I said, I'm going to be extending you guys a bit, so this part is not, what I'm saying right now, is not going to be in your exam. It's important to know about global mins and global maxes, but where they come from is not going to be in your exam. But assume for some reason that this function was a profit function, this cubic function. And say you're at your school and you're selling lemonade, right? And all of these are the, so say, let's put that in here, and say, on the x-axis, this is the amount of lemonades you sell. And this is the rand you make in profit. Well, if we're being realistic here, you can't sell negative amounts of lemonades, can you? Right? So clearly, the function has an asymptote. Or not really an asymptote, sorry, the function has an endpoint. Yeah. Because you cannot sell less than 0 lemonade. And say hypothetically, in the world, you know, this is not necessary, but if we're saying, hypothetically in the world, there might only be a certain amount of lemonade, like amount of lemons, for example, or whatever ingredients you use in your lemonade. So there's a hypothetical maximum. Let's just call that pi. Right? You've got two limits to your function now. Realistically, you can't sell less than 0 lemonades, and you can't sell more than pi lemonades. So now, you look, well here, the limit that you've applied is also right, on the local minima, or just to the left of the local minima, actually, sorry. I drew, this should be on -1, right? But it's to the left of the local minima, or to the right of the local minima, sorry, because the local minima is at -1, so this is on the origin. So assume that this is the stationary point at -1. I know it doesn't look like that graphically, but just assume that. Well then, your new stationary point, or your new global, sorry, not your new stationary point, your new global minimum is this point here. Which in real life, considering that everything off the stationary point increases, even though I know the graph doesn't look like that, this will be higher than your local minimum. Because in actual fact, you can't achieve that local minimum, you can't solve negative lemonade. So this would become your new global minimum. Similarly, this tends to infinity. If you kept selling more lemonades, you make more profit. Clearly, lemonades are a profitable business, but you can only sell so many lemonades. So if you're a profit maximizing seller, you'd sell as many lemonades as you can and maximize your profit. Because this is your global max. It's the highest that you can achieve. So this is what I mean by endpoints. How endpoints would create a global maximum or global minimum. Another example would be, we look at parabolas. If you recall earlier, I told you that this point and this point are both global minima and global maxima. The reason they're global has nothing to do with endpoints. Clearly in both directions, it tends to positive or negative infinity depending on the leading coefficient, right? But the difference in this case is the concavity of the functions is constant across both functions, right? This is because the second derivative is a constant. Remember what we did earlier? If it was x squared or negative x squared, the second derivative would be 2 or -2. It's a constant. Whereas if it was a cubic, if it was x cubed, then this would have x in it. So what that means is, for a parabola, the second derivative is constant for a quadratic function, which means the concavity of the function is constant. So this function is always convex, and this function is always concave, which means there's no way on the function that you can go lower than this value, and there's no way on the function where you can go higher than this value. So for a quadratic function, the stationary point is necessarily a global minima or a global maxima. So those are the two cases where you have a stationary point. I'm not quite sure if the syllabus would ask, but if it did, when you classify a stationary point for sure, the syllabus will ask this, remember to write a local minima or local maxima, other way around, local max and local min, unless there's either endpoints or constant concavity, which at NSC level will only be in quadratic functions. So yeah, that's how you, so firstly, you find stationary points, set the first derivative equal to 0. Step 2, you classify them either graphically by observing what the function does before and after the stationary point, and observing the second derivative test, or sorry, the classification test, or you observe the second derivative test and see, well, if the second derivative is positive, I've got a minimum. If it's negative, I've got a maximum. If it's 0, I've got a point of inflection. And when you're looking about whether they're local or global minimum maxima, look at endpoints or look for constant concavity, in other words, a quadratic function. For points of inflection, recall it cannot be a global or minimum point of inflection, sorry, global or local, because the point of inflection just tells you a change in concavity.